Dr. Fillipenko is an astronomer with the University of California at Berkeley. He received his BA in physics from UC Santa Barbara and his PhD in astronomy from Caltech. He then became a Miller postdoctoral fellow at the University of California at Berkeley. In 1986, he joined the faculty at UC Berkeley, where he remained through the present time. Very impressive bio. I've got to read this all to you because he's embarrassed, but that's okay. We've got a very distinguished guest in our midst tonight. I've got to say these things. He's an observational astronomer. He makes actually frequent use of the Hubble Space Telescope and the Keck 10-meter telescopes. His primary areas of research are supernovae, active galaxies, black holes, and cosmology. He's also spearheaded efforts to develop robotic telescopes for CCD imaging. His research accomplishments, documented in over 290 published articles, have been recognized by several major awards. For example, the AAS Pierce Prize, the Canadian Astronomical Society Petrie Prize, and the Guggenheim Fellowship. A dedicated and enthusiastic instructor, Dr. Fillipenko has won the top teaching awards at UC Berkeley, and in 1995 was voted the best professor on campus. In an informal student poll, students are saying this. He's got to be good. In 1998, he produced a 40-lecture video course on introductory astronomy with the teaching company. Now, if you're wondering if he's got any time left over for anything else, well, yeah, let me tell you, it's probably filled with his two children. He's got a child 4 and a child 6. He loves tennis, hiking, world travel, and every couple of years, he, as well as thousands of other people, including myself, will gather together some weird place on our planet to bask in the corona. He also is addicted to solar eclipses, as I am. Please join me in welcoming our very distinguished guest, Dr. Alex Fillipenko.
Well, thank you, Dennis. It's really a great pleasure to be here. I really love San Diego. I spent some time here after my junior year in high school, in fact, at a chemistry program of all things at San Diego State University. And then as a freshman in college, somewhere along the way, I saw the light and switched to physics with the intention of becoming an astronomer. So I still like chemistry, and I have great memories of my summer at San Diego State and all the fun times we had getting ready for college, basically, you know. Anyway, I think it's great that Dennis puts on this series, and that everyone has a chance to see astronomy as it really occurs. And you get some of this in magazines like Sky and Telescope and all that. But there's really something to be said for having people who are doing astronomy tell you about their research, because the research is easily as addictive as total solar eclipses are. And I'm just so happy to have been given a chance to pursue research. I'll be telling you today about stellar explosions, okay? Some stars undergo gigantic explosions at the end of their lives. And I want to tell you what meaning these have for us, for the universe. And later on, as Dennis mentioned, on April 8th, I'll be giving a shop lecture, or the shop lecture, where I'll discuss the utility of these exploding stars for cosmology, for studies of the expansion of the universe and the birth and evolution of structure in the universe. So I hope you'll be able to make it to that. This is a picture just of the sun, and our sun, through a filter, looks yellow. It's actually quite a white color if you look at it, and don't blind yourself. And the easiest way to look at it and to get an appreciation for its blindingly white color is to look actually at a total solar eclipse. And in the last few seconds before totality and the first few seconds after totality, you can actually see how white it appears to be. Normally we see pictures like this and it looks yellow through a filter or reddish orange near the horizon while it's setting. And that's of course because dust and stuff in our atmosphere tends to extinguish or absorb and scatter away the blue light more than the red light. But it's the normal star. It's got one solar mass of material by definition, and it's generating energy in its interior right now through nuclear reactions, and that can keep it going in its present pretty stable state for about 10 billion years. It's roughly halfway through its stable lifetime. That's not to say that life on Earth will be pleasant for the remaining 5.5 or so billion years, because it turns out that though the sun is stable to a first approximation, it is gradually getting brighter and brighter. And in fact, in about 1 billion years or so, this place will become rather unpleasant to live on. In particular, oceans will evaporate away. And it's going to be tough without liquid water to remain here on Earth. So if we survive for the next 1 billion years, we had better get out of here and at least move to Mars. But that doesn't buy us too much more time, right? The sun will be unstable by then. It'll turn into a red giant, something like this, much bigger than it really is right now. We don't really want to move to Mars at that point. We want to move to another more stable planetary system. Okay, so it'll become big and much more luminous, much more powerful than it is right now. Everything on Earth will be fried. And then, that's not too comforting a thought, but again, I think humans have far more pressing issues to deal with in the next 1 billion years, you know. Anyway, it'll then undergo a few sort of gentle puffs, gentle burps, I like to call them, where it'll expel its outer layers of gas sort of gently into the cosmos. And what will be left behind is this dying ember of our sun. We know this because we can see other stars at more advanced stages of their evolution, and they're doing effectively what our sun will do. If we think our sun is a typical star, then finding stars of a similar mass and seeing how they behave should tell us, roughly speaking, how our sun will behave in the future. And this is how, with some degree of confidence, astronomers can say this sort of thing. So it'll become what to astronomers is called a planetary nebula, not because it has anything to do with planets per se, but because through the small telescopes with which Herschel and other early astronomers looked at the heavens, these things looked like disks and like planets, basically. They couldn't, in some cases, tell that there was a hole in the middle. But really, this is sort of a balloon-shaped thing, or a shell. And there can be many such eruptions, and gradually, our sun will whittle away about half of its material through such eruptions. And what will remain in the center, then, is a tiny little star called a white dwarf. And an excellent example of a white dwarf is Sirius B, the companion to Sirius, the brightest star in the sky. Now, with your naked eye, you can't tell that Sirius, the bright star out there, has a companion, but it does. It does have a companion, and it's one of these very evolved stars. It's called a white dwarf. You can see that in the case of Sirius B, it's actually a little bit smaller than the Earth. And this shows the Earth and Sirius B in comparison with the Sun. The Sun is about 110 Earth diameters in diameter, okay? And the white dwarf is about the size of the Earth. And it's a very strange sort of material. It's called, the stuff of which it's made is called degenerate matter. Not because it's morally reprehensible or anything like that, but that's just the term that quantum physicists have for a sort of material that's unlike bricks or clay or wood or anything like that. It has very weird properties, like the more massive a white dwarf, the smaller it is. And that definitely is not the way houses and bricks and things are. You know, usually the more massive they are, the bigger they are. All right? But this degenerate material is really weird stuff. And I could digress and tell you all about the wonderful world of quantum physics, but suffice it to say for right now that this is really crazy stuff, and it's very dense. A teaspoon of it would weigh several tons, all right? So very weird stuff. Anyway, our own sun will die in a relatively quiet way. This thing generates no new energy through nuclear reactions. It will just, for billions of years, cool down and emit, radiate, whatever heat energy is trapped inside it. And a lot of heat energy did get trapped inside, or will have been trapped inside by that time, due to all the nuclear reactions that the sun went through over the course of 10 billion years. But the white dwarf itself is not generating any new energy. It's a retired star. It's spending its life savings, I like to say, okay? And it'll just gradually cool down and become dimmer and dimmer, and at some point we call it a black dwarf because it's just too dim to see. So that's the sort of the future of our sun and the future of most stars, relatively low mass stars. But some stars, in particular, the very massive ones, go out in a tremendous burst of glory. They're not satisfied to go out with a little whimper like this, producing a few little burps and planetary nebulae, pretty as they are, you know. This isn't enough for some stars. So some stars blow up completely. And you might not be able to see the bottom panel, but all it shows is what the star used to look like before it blew up. And it was about the same brightness as any one of these here. There's a typical star in this region here, and then it blew up and became billions of times, or in this case actually a few 100 million times brighter than it was before. So it's a tremendous explosion. These explosions are among the biggest explosions we know of since the Big Bang. Now, many of you have heard about gamma ray bursts, which is another hot new field. They may or may not be more intrinsically powerful. It depends on whether a gamma ray burst is essentially a laser beam pointed towards you and shining very little in other directions. In that case, it's only about as powerful as a supernova, an exploding star. Or if it radiates as much in all directions as the direction in which we see, then clearly the total radiation is a lot more, and gamma ray bursts become more powerful even than supernovae. But that's still debatable. In any case, these are among the most powerful explosions in the universe, and who among us doesn't enjoy a good 4th of July fireworks show viewed from a safe distance, okay? So anyway, they're neat and exciting things, and you're actually seeing something change on a human timescale in a star, which you don't expect usually for the sun, nor do we really want the sun to change much on a human timescale, okay? But besides being exciting, they're actually astrophysically very important. First of all, they give rise to bizarre creatures like neutron stars and black holes, and I'll have more to say about them later. So they give rise to states of matter which are very difficult, if not impossible, to reproduce on any macroscopic large scale in our laboratories. Second of all, they send shock waves, waves of compression, through the rarefied gases between stars, and they can actually nudge a cloud of gas, a nebula, which is on the brink of gravitational instability. That can be nudged by one of these pressure waves into a state of gravitational contraction. And so the death of one star can lead or help trigger the birth of new generations of stars. So that's an important aspect of them as well. They also heat up the gas in galaxies, and it flies out in big, magnificent galactic fountains and stuff. They also produce cosmic rays, some of which do make it through Earth's atmosphere and cause mutations in cells on Earth. And too many such things is not good, but some number of such things is good because we believe it leads to evolution. And since this isn't Kansas, I don't have to feel too bad about saying this, you know. So my apologies to anyone from God's country. But anyway, so they're also very useful for cosmology, this study of the universe as a whole and its expansion and its overall history. Because they're so intrinsically powerful, you can see them at a very great distance, and you can use them to measure distances, because basically you know how bright it should be, that is, if it were nearby, and you measure how bright it appears to be, and that then, by the inverse square law, gives you a distance. Just like looking at a pair of headlights at night on the highway. You judge the distance of the oncoming car, in part by how bright the headlights appear to be, and also in part by how much of a separation the headlights appear to have. Okay, so they're really useful for cosmology. For the purposes of this talk, though, if there's one thing you come away with from this evening, it's that we are made of star stuff, and it's largely as a result of supernovae that this star stuff becomes available as the raw material from which Earth and rocky planets are formed. So, in the evolution of the star prior to its explosion, it's fusing hydrogen to helium, helium to carbon and oxygen to progressively heavier elements. In other words, the ashes of one set of nuclear reactions becomes the fuel for the next set. We have very good evidence that the universe was basically born only with hydrogen and helium, to a very good approximation. All the rest of the stuff was built up inside stars. And our sun right now is fusing hydrogen to helium. Later, it'll fuse helium to carbon and oxygen. But if all stars were like our sun and did not blow up, then those heavy elements, which were so patiently generated during the star's life, would not become available for the purposes of producing new stars, planets, and things like that. So they would remain forever locked up deep in the interiors of stars. So it's these explosions that let loose these heavy elements, and it's the explosions themselves which also produce, during the act of exploding, a lot of these heavy elements. So what happens is these chemically enriched gases go flying away from the supernova, This is now after a couple of hundred years. That's what the picture looks like. And these are not just hydrogen and helium anymore. They have carbon and oxygen and calcium and iron, things which are necessary for life on Earth. Over the course of tens of thousands of years, these ejected gases spread out, okay, become wispy, merge with other wisps, either pre-existing wisps of gas that had never been in stars and which are therefore primarily hydrogen and helium, or maybe wisps from other previous generations of exploded stars. And these wisps come together, eventually form a gravitationally bound nebula, and then the central part of that nebula starts gravitationally contracting, perhaps with the help of a supernova nearby, which gives it a little bit of a kick. And then new stars form in the central regions. And this is a nebula with which I'm sure many of you are familiar. This is the famous Orion Nebula in the Sword of Orion, the Great Hunter. And we can tell from studies of this little cluster of stars in the middle that these are very young stars. They're only a few million years old. That may sound a long time to you compared to next Tuesday, especially if you have an exam then or something like that. You know, I like to tell my students. But on a cosmic scale of things, that's very short. And in fact, even compared to our own sun's current life or current age of around 4.5 billion years, that's very short. So these are very young new stars, and they are chemically enriched stars because they are forming recently, or have formed recently, from gas that has had a chance to become chemically enriched through many previous generations of exploding stars. And when we look with Hubble, for example, at the central regions of the Orion Nebula, we can see all sorts of newly formed stars and stars which are still in the process of forming. These stars are not even yet settled down to a quiescent state of existence. And notice these dark disks around them. We think that those are leftover gas and dust that did not get incorporated into the star. Instead, it has a chance of being incorporated in planets. And indeed, we think planets form quite naturally as a result of the process of star formation. And indeed, my colleagues, there should be these chemically enriched stars or planets like Earth and stuff around stars that are forming from chemically enriched gas. We think these planets are probably there. We have not actually detected Earth-like planets, but my colleagues Jeff Marcy and Paul Butler at Berkeley, using the telescopes at Lick Observatory, have been the foremost hunters for and finders of planets around other stars. So far, they've only found Jupiter-sized objects and somewhat bigger. That's just because the technology is not yet good enough to reveal small, rocky Earths. But the fact that they're finding big Jupiters suggests that indeed the process of planet formation is a typical one, typical of other stars in our galaxy, and probably there are Earth-like planets as well. And this, of course, then raises the whole issue of whether we're alone in the universe. You know, big headlines, is anybody out there? This was when the first two so-called extrasolar planets were discovered a few years ago. How the discovery of two planets brings us closer to solving the most profound mystery of the cosmos. I mean, this is really pretty mind-boggling stuff. Now they've got 30 planets or so. And maybe one of these days, NASA will build a big enough telescope that we'll see, if not a smiling face on one of them, then at least a continent and some oceans and stuff, okay? Well, you might say, okay, gee whiz, actually, finding planets is an interesting thing to do, but don't we already know the answer to this question? Is there anybody out there? After all, we're inundated with irrefutable evidence that there are not just little protozoans and stuff out there, but even intelligent creatures and stuff, So you could argue whether there's any evidence for intelligence in this photograph, I guess, but I don't know, Oh gosh, I get a real kick out of plate magazines like the Weekly World News. I buy them occasionally just to cheer me up because they're so funny. And then after a while, I get depressed because I realize that millions of people actually believe this hogwash, okay? So what also gets me is how come they don't get sued more often, or is it just not worth Bill's time? He knows what it's been on the receiving end of being, anyway. So, okay, so, all right, well, anyway. Don't believe everything you read, even in the astrophysical journal sometimes. But the main point of this is that supernovae are the things that get rid of this stuff from the central parts of stars, and also the very act of explosion produces a lot of heavy elements as well. And these then mix with other gases and form new planets, rocky planets perhaps, and in some cases even life. And so this is what Sagan meant when he said we are made of star stuff. He did not discover this, but he did a very effective job in trying to bring across this one central discovery of astronomy, which of all the discoveries in astronomy, this is certainly one of the most important, that we can say without much doubt at all, and I'll give you the evidence later today, we can say without much doubt that the heavy elements in your body really used to be in stars, and indeed were cooked up by stars. And that's just one of the most amazing thoughts I've ever come across. So I'd like to dedicate this talk to the memory of Carl Sagan, in fact, who did such an effective job in popularizing astronomy. Okay, well, so supernovae occur among just a minority of stars. And to give you some idea of that, a typical big galaxy, here's one that looks much like what we think our Milky Way galaxy would look like if we could see it from the outside. It consists of a few 100 billion stars, and it's about 100,000 light years across, which of course means that if you were on a planet orbiting a star here, and you wanted to send a message to a friend orbiting a star here, saying, hey, let's go have a beer after work, it would take 100,000 years traveling at the speed of light for your light signal to reach that. Radio waves do the same thing, all travels at the speed of light. And even if your friend were to reply right away, yeah, let's go to the pub down the road or whatever, it would be a total round trip communication time of 200,000 years. Hardly a stimulating conversation, but that's just the way the universe is built, okay? So anyway, lots of stars, lots of distance between the stars. Only one, typically, of these stars will explode per century, okay? That's how rare supernovae are, all right? Now, I want to study them. I want to understand, how is iron built up? How is oxygen built up? Does it leave behind a neutron star? Does it leave a black hole? Does it leave nothing? What kinds of stars do this? I want to learn these things. So I want to study as many of these exploding stars as possible. So we need to look for them, and they're rare, and it's like trying to find a two-headed snake. They exist, but you're unlikely to find one in your own backyard. So you have to look in other people's backyards, in which case you'll probably be at some point accused of being a peeping Tom or something. But anyway, we can look at these other galaxies and hope to increase our chances for finding supernovae. So how do you do it? You look at lots of galaxies, you take pictures of them, for example, and you look for arrows in the sky. And that's how you find supernovae. Look at that. 4 out of 4. This also shows you how bright they are compared to a whole galaxy of stars. They can be comparably bright to a small galaxy, 10 billion stars. They're about 1/10 of a bigger galaxy. Anyway, yeah, so obviously it's not this easy. You have to take several pictures, and then eventually an arrow pops up, right? So there isn't an arrow there, and there is one there. So, and of course, among amateur astronomers, one of my heroes when I was growing up was the Reverend Robert Evans. He single-handedly has found several dozen of these things. He memorizes what these fields look like, and then he hops from one field to another very efficiently during the night, compares the image that he sees through his eyepiece with what his brain tells him that the field should look like, and occasionally there's a new object there, and he reports that as a supernova candidate, and he's been phenomenally successful in this game, and indeed, he was and still is actually one of my heroes. But I don't know, I like to sleep at night and stuff. Plus, he has this deep connection. His job in real life sort of is, he's a pastor, okay, at the United Something Church of Australia. And he tells me that he sometimes has this premonition that a particular night he should make a real effort to observe, because that's the night that there's going to be a good supernova, And I don't have this direct line to God, so I've got to do it more by brute force. But I like to sleep, so we have this robotic telescope at Lick Observatory, which is about an hour's drive east of San Jose. There it is, right there. It's just a 30-inch diameter telescope, which isn't that big by professional standards. But it fills a very important niche, because I've got this thing completely programmed to take all my data and do some of the analysis. And next year we're going to program it to write our papers for us. And what I really wanted to do is to write our grant proposals so I can go off to Tahiti or something like that. No, seriously, I spend all my time raising funds for my group of 10 or 12 people. And so I actually play with light, with the photons, painfully little. And gosh, what I really need is an endowment of 2 million or something like that. And then we could do it. And we would spend more time working on the data or going off to Tahiti. But for right now, it finds these supernovae, okay? And that saves me a lot of time. Here it is, close up. And in recent years, we've had smashing success, basically because I hired an excellent postdoctoral fellow. I brought him in from China because I noticed a few years ago that, first of all, he was the first Chinese astronomer to have discovered a supernova in about 1,000 years, since the year 1054. Some of you will recognize as being the origin of the Crab Nebula, okay, a great supernova in 1054. So he found one, then he found a bunch, and in 1997, his group at the Beijing Astronomical Observatory found 15 supernovae, which was a world's record for any one group to find 15 in a calendar year. So I figured, I got to get this guy over to my group, maybe he can work wonders. And he did. In 1998, we found 19 of them, and in 1999, we found 40 of them, and we found the first one of the millennium. And if you don't think that this was the beginning of a new millennium, we aim to find the first one next year too, so we'll have them all covered. So not only has our work skyrocketed, but interestingly, the Beijing group's work has plummeted ever since he left. And the best way to succeed in business is to hire away your best competition, And so anyway, not that I wish them ill. In fact, we're now collaborating to get them back going because they're sort of a developing country in astronomy, and I certainly did not want to make their work go downhill. But he's just been wonderful. Wei Dong Li is his name. So he got this thing to work really well, and he ran tons of programs to get the whole thing to work. And here's one that we found in 1999. It was, in fact, the 30th one of that year that we found, and that doubled the Beijing record. And so we thought that was quite an accomplishment. And plus, this one was a really good one, because not only did it have an arrow, but it was only 25 million light years away, and that's pretty nearby compared to most galaxies. Most galaxies in which we find exploding stars are, many tens of millions of light years away, if not 100 million light years away. Why? Because there's more galaxies out there. The bigger the volume of space, the more galaxies you survey, the greater is the chance that you're going to find a supernova. Most people on Earth are not in this room, okay? Most are far away. Some not even in San Diego. So, all right, so this is an interesting one. And then we not only find these things, but we measure how much they brighten with time and fade with time. So here's plotting brightness in some weird units, and this is time. And you can see that they brighten and fade. They're magnitudes for those of you who like magnitudes. And the shape of this curve tells us about the physics of the explosion and all this sort of stuff. And so we try to analyze this and try to tell us, it's trying to tell us really what the star is doing while it's exploding. The other thing we do is we take bigger telescopes, like the 3-meter telescope at Lick Observatory, with which Jeff Marcy and Paul Butler discovered all these planets. And they look at bright stars and really look in detail at small parts of the spectrum. Our stars are faint, even these relatively nearby supernovae, and so we don't spread the light out very much, but we spread it out to some extent by passing it through a prism or the equivalent, and that gives us a rainbow, a spectrum. And if you measure the brightness of the light at different colors, blue through red, and you plot like brightness versus color, or wavelength of light is what this corresponds to, you get what's called a spectrum, not just in astronomy, but in all sciences, that's what's called a spectrum. And the spectrum can tell us all sorts of groovy things about the star. Its temperature, the speed with which it's exploding, its chemical composition, all sorts of great stuff comes from the spectrum. A lot of astronomy is done with just pictures. I'm not knocking pictures, but a lot of the astrophysics is done with the actual spectra, it turns out. You need both, really. They're complementary. And the pictures are much easier to show. So how often do you see front page news with a Hubble Space Telescope spectrum? Not very often. The newspapers know what it takes to sell, and if you show some spectrum above the fold, you're not going to sell many issues, even of really good newspapers, that sort of are different from the weekly world news and stuff. So anyway, so let me show you just a spectrum or two. Here's brightness or intensity versus wavelength. And we find that these exploding stars, by and large, come in two flavors. Basically two flavors. There's more than that, but let me just concentrate on two. Astronomers, in their rather unimaginative way, call these type 1 and type 2. They could have called them Fred and Jean or something like that, but no, they call them type 1 and type 2. They both look like roller coasters. And the interesting thing about the type 1s is they have no hydrogen. There's silicon and sulfur and iron, magnesium, calcium, oxygen. That's the stuff that the supernova actually fused during the actual explosion. So these are newly synthesized elements. Just fantastic. We're seeing element creation here. All right? But there's no hydrogen, and that's quite strange because most of the universe's matter, by a long shot, is hydrogen. Most of our sun's mass is hydrogen. Okay? And to find stars that don't have hydrogen is rather remarkable. The other kind does have hydrogen. This bump here is due to hydrogen. It also has oxygen and calcium and iron and stuff like that. But they're spectroscopically distinguishable. So what produces these two types? Okay, well the type 1s are thought to be one of these white dwarf things, like what our sun will turn into in about 5 or 6 billion years. But in the case of our sun, it'll just sort of whimper away and become a black dwarf eventually. If, however, you have a star in a bound system with another star, and if they're close enough together, then this white dwarf can steal material from the other star, and its mass, under some circumstances, not all, but some circumstances, can grow. I say not all because occasionally it can eject the material that it got through a small surface explosion called a nova. A regular nova is just a surface explosion. And in that case, the white dwarf's mass doesn't actually grow because stuff blopped on, but then it got expelled away, and so you had no net gain. But in some cases, the accretion, as it's called, can be steady enough that the white dwarf's mass increases. As the mass increases, because the thing is made out of this weird degenerate material, its size actually decreases. And at some point, it becomes unstable. And a young scholar on his way from India to England, where he was to be educated, this is Chandrasekhar, figured this out on the long voyage from India to England. He figured out that there can be only a limiting certain mass to these white dwarfs, at which point they have to become unstable. He didn't know what would happen to the white dwarf. He didn't know whether it would explode or implode or what, but he knew that it has to be unstable, and many decades later, he won the Nobel Prize for this work that he did as a youngster of 21 or something. Okay, well, you get this colossal explosion is what happens when you reach this Chandrasekhar limit of around 1.5 times the mass of our sun. What happens is the carbon and oxygen nuclei in the white dwarf start hitting each other because they're close enough together because this thing's squished into such a small volume. And then the energy that they release through nuclear fusion goes into making the neighboring nuclei hit each other with ever greater violence. And they then all go off in one big shebang. It doesn't readjust itself the way a normal star would if you put a propane torch in the middle of our sun. Actually, a propane torch wouldn't cut much mustard in the middle of our sun, but if you put a big, huge Ace Hardware propane torch in the middle of our sun would readjust its structure because it has a new energy source. But degenerate matter cannot do this because it's degenerate, and I can't go into this right now, but it doesn't adjust itself, it instead blows up. So what you have then is a completely disintegrated star. No compact remnant is left over, or so the theory goes, and you have this balloon of chemically enriched ejected gases spewing out into the cosmos, in some cases perhaps producing new stars and planets far into the future. So that's a type 1, and those are the kind that are of greatest utility for cosmology and about which I'll be talking about in the shop thing. The other ones, type 2, come from a very different kind of a star, an initially much, much more massive star, and it's in an advanced stage of its career called a red supergiant. And the best example is Betelgeuse in the shoulder of Orion, and there are probably as many pronunciations for that as there are astronomers, and then some. But anyway, Betelgeuse is kind of a funny name, so I like to call it Betelgeuse. It's a red supergiant, and it's going to blow up at some point in the next 300,000 to 500,000 years. We just don't know when, because you can't really tell from the surface layers precisely at what stage the center of the star is at. And I'll show you in the middle that it's the center of the star that's the important thing here. Anyway, this thing is huge. Here is the size of the star, and actually here is Earth's orbit, there, right? And Jupiter's orbit is about yay big. So this particular one is admittedly a rather large one, even for a red supergiant, but it's the size of Jupiter's orbit. So these are huge stars. Our own sun will never become quite this big. It'll become perhaps as big as the orbit of Mercury or something, okay? Anyway, these are fantastic stars. They're very massive stars. They start out with 10 to 40 times the mass of our sun, and they've gone through a bunch of stages of nuclear burning. In our sun, hydrogen will go to helium, and eventually, when it's a red giant, helium will become carbon and oxygen in the very center. But our sun doesn't have enough mass to compress the carbon and oxygen and get them to fuse any further. So that's where our sun will end. But big massive stars like this can undergo several more stages of nuclear burning. And the carbon and oxygen basically become oxygen, neon, and magnesium. That then produces silicon and sulfur, and eventually you get iron, Fe. And iron is the most stable, the most tightly bound of all atomic nuclei. So fusion of iron into still heavier elements does not release energy, rather it requires energy. So a star does itself no good whatsoever fusing iron to heavier things. A star is trying to stay alive. It's trying to stay puffed up. And the way it does this against the relentless, or almost relentless for much of its life, force of gravity is by keeping hot inside. And it does this by fusing light elements into heavier ones. If that fusion robs the star of energy, that'll simply accelerate the collapse of the star. And the star doesn't want to do that. You might ask why. And it has to do with thermodynamic and other reasons, all right? It's not, we put this in anthropocentric terms, it doesn't want to do that and all that, as though it had a choice. Well, it doesn't have a choice because of the laws of physics, basically. And so it ends up not fusing the iron into anything heavier because it wouldn't do it any good. Well, that can't continue forever. The iron core becomes more and more massive. This actually occurs in the last few days of the star's life, very short-lived stage. And when the iron core reaches about 1.5 times the mass of the sun, comparable to the Chandrasekhar limit of a white dwarf, it basically says, look, I can't hold up all this stuff above me anymore. I'm just going to quit. I'm going to collapse. So the iron core implodes. And you might say, whoa, wait. I thought we were talking about explosions here, and here I'm talking about an implosion. Well, wait. Yes, the iron core implodes, but the protons and electrons actually combine to form neutrons and weird little particles called neutrinos, okay? And the neutrinos can just escape. They hardly interact with anything at all. You've only got a 50-50 chance if you're a neutrino of hitting a piece of lead while going through a light year of lead, okay? They're not very interactive particles, okay? So they just go screaming out of the sun at about the speed of light. They don't go faster than light or anything like that, but it's simply that they don't interact. So they go screaming out right away. The neutrons are left behind, and indeed, they're in such a compressed state that that's basically a neutron star. This is the birth of a neutron star. But what happens is there's a rebound effect. Think of what happens when you jump onto a trampoline. You don't just go ka-chunk, and reach equilibrium right away. No, you bounce back up, and then you oscillate a few times and you dissipate energy and eventually you come to rest. Well, in a similar way, as all these neutrons are forming and collapsing down, they don't collapse and form a stable configuration right away. They rebound. They overshoot a little bit and then they rebound. And during the rebound, they then hit the stuff that surrounds them that's still falling in, and that propels that material out. Now, admittedly, you get a little bit of help from the neutrinos, substantial help. But I can't illustrate neutrino interactions very well, so let me at least illustrate the bounce for you. This official NBA basket small, bouncing off of this floor here, is like the neutron star forming and bouncing off of itself. I'm supposed to stay in the light because this is being filmed. All right? So I can't make it collapse in on itself, so the next best thing I can do is just make it bounce off the floor. Okay, so left to its own devices, it doesn't quite bounce as high as the height from which I started it because it loses some energy during the bounce. This tennis ball will be the material that's falling around the collapsing neutron star, and it too does not bounce all that high. But if I put one on top of the other, see what happens, all right? In fact, you can even aim it. Now, I know Herb because we were on an eclipse trip in Thailand in 1995, and Herb's in the front row. but I'm going to aim it at someone in the back there. And, like, well, I didn't do that very well either. But in my class at Cal, I can aim this quite far, that did that. I have a lot of these things here. Here's another one. Dennis mentioned I like to play tennis, so there we go. There, yeah, you can keep the ball. So you get this thing. Now, the catch is, of course, I used a very small tennis ball, and I had a medium-sized basketball, and so I gave this thing a lot of energy. Normally, of course, the star has all this stuff that's falling in, and only 1.4 solar masses, or the neutron star, and you've got 7 or 8 solar masses on top of it. So the explosion fizzles. Okay, I didn't tell you the whole truth. But the flood of neutrinos that's produced gives the thing an extra kick and causes the explosion to be successful. But the bounce thing is just so counterintuitive until you've seen it that I thought I'd show it. All right, so from an implosion, you actually get an explosion and the birth of a neutron star. And if there's enough fallback of material onto that neutron star after its birth, maybe the neutron star goes on and collapses still further to form a black hole. Okay? Neutron stars can only have a certain limiting mass as well. That's analogous to the Chandrasekhar limit. Okay? And that's not as well known. It's somewhere between 2 and 3 solar masses. The properties of neutron material are less well known than the properties of white dwarf material. Okay, well, this basic scenario was first postulated by a rather abrasive astronomer at Caltech, Fritz Zwicky. Now, Fritz Zwicky is one of my heroes because he was so far ahead of his time. Many of you know about dark matter and the stuff that pervades our universe. He actually thought it up decades ago. He was the one who said that this is what's happening to the core of a massive star when it goes supernova. And here he's probably trying to illustrate this point to his dimmer Caltech colleagues. What's going on in the middle of a star? He had brilliant ideas. The trouble was he was very abrasive and basically thought everyone else was a dummy. And you don't get along very well with people if you imply to them, you insult them at every moment. And my own advisor, Wal Sargent at Caltech, actually got along very well with him. I unfortunately never met Fritz, but Wal was one of the people who actually did get along with him. Maybe he has a thick enough skin or something. But I think Fritz was an amazing fellow. So he's the one who basically predicted that the birth of neutron stars is the process of a big star going supernova by this process that I've just described. And here David Arnett, formerly of Chicago, now at Arizona, is showing you what the Sears Tower in Chicago would look like if compressed to the density, the mass per unit volume of a neutron star. It would be this little gumball here. Now, before doing this experiment, it is advisable to evacuate the building, okay? Or else you have all these people squished in a gumball and stuff. So maybe that's why he got fired from Chicago and went over to Arizona or something like that. So no, he left of his own volition. So anyway, it's really dense material, and we have no way of producing large quantities of such material in laboratories. These are basically atomic nuclei, but they're big ones, like size of this table or the size of a city. The neutron star is maybe 10 kilometers in radius, something like San Diego, okay? Maybe greater San Diego. And yet it has the mass of our sun, even more than that, 1.5 times that mass. So it's amazingly dense material. It's essentially a gigantic nucleus. And then during this rebound in a type 2, you have all sorts of nuclear reactions and stuff going on because there's all this turbulent hot gas coming outwards, almost in bomb-shaped, mushroom clouds almost like. But anyway, there's a lot of nucleosynthesis going on, all right, in a type 2. So the prediction of theory is that type 1s come from these white dwarfs. They leave nothing behind. They produce heavy chemical elements, but they don't have much of a way of producing neutrinos. A type 2 comes from a massive star, a supergiant, whose core collapses, produces a neutron star and neutrinos, and in the process synthesizes a whole bunch of heavy elements. So this is what we want to test. Okay, this is the theory that's been built up as a result of having seen a whole bunch of supernovae that are maybe a few tens of millions of light years away. But what we'd really like is a nearby one. Kepler saw a nearby one in 1604, but that was right around when the telescope was being invented. He did not use a telescope, in fact, to study his supernova of 1604, and no modern day instruments existed back then. So that was just a purely visually observed supernova. His mentor, Tycho Brahe, observed one in 1572. They were lucky. They were just 34 years apart. Since then, there's been maybe one that's been seen in 1670 or so, but that one was not very well observed, and we've been basically sitting around waiting. That's not to say that they haven't occurred. Here's our Milky Way down here, and those of you who have seen the Milky Way from a dark mountain site on a clear moonless night have undoubtedly seen splotches in it, especially in the Scorpius-Sagittarius region and the great rift in Cygnus. It's a splotchy thing, the Milky Way is. There's a lot of gas and dust along the way. And in fact, we can't see very far along the plane of our galaxy because it's all been, absorbed by all the dust and stuff. So there's probably been some that we've simply missed. But there are two satellite galaxies of our own Milky Way galaxy that are about 170,000 and 210,000 light years away. A mere stone's throw for astronomers, but upwards from the Milky Way in a relatively unobscured region surrounding our galaxy. These are the clouds of Magellan. They were known long before Magellan, of course, but I guess this indicates the influence of Western Europe at the time of his great voyages. The Large Magellanic Cloud and the Small Magellanic Cloud. And the Large Magellanic Cloud has this thing here called the Tarantula Nebula. Kind of looks like a tarantula. It's the biggest stellar nursery that we know of in our local group of galaxies. There's a lot of stars currently being born there, and there's been a lot of stars born there in the past 100 million years. It's just a great stellar nursery, a factory. Now, it turns out that the big massive stars, despite having a lot of fuel to burn, they burn it at a profligate rate, and they use up their material very quickly. So our sun will live relatively stably for 10 billion years, but a 15 solar mass star lives only for 10 million years or so. Very short lives. They live vigorously and die young, basically, like in a Ferrari or something. So we expect massive stars to be dying roughly where they are being born, simply because there's not enough time for them to move away from their birthplace. Our sun has long since moved away from its birthplace. We don't know exactly where our sun was born. But big stars die basically where they were born. So you might expect stars to explode here. And indeed, in 1987, there it is. The first one of 1987, so it's called Supernova 1987A, it occurred in the outskirts of this great Tarantula Nebula. So astronomers have been waiting pretty much 400 years for this thing. Plus 170,000, of course, but we couldn't know that it was coming, is the point. And we hadn't had a good one in 4 centuries, so it was a great chance to study the stellar explosion process. And so monumental was this event that it made the cover of Time magazine. A star explodes, providing new clues to the nature of the universe. More important than the Israel spy case fear, because things like that happen every day, but how often does a star explode in your own backyard, but still from a comfortable distance? So it was a great thing. And it was first discovered by a student in Chile, a student from the University of Toronto, who was using this telescope here to study variable stars in the Large Magellanic Cloud. And he had just started this project. It was his second night ever. February 24th, 1987. And on his first photograph, he took a nice picture. Then his second photograph, the next night, he took what he thought was a good picture, but then the wind blew the shed in which the telescope sits. It blew it shut, so he figured, okay, that's enough for the night. So he developed the photograph, and he looked at it in real time before the sun had come up, and he noticed a dark splotch in the negative of this plate. And that splotch hadn't been there the previous night of the very same region of the sky. And it didn't look like a plate flaw, like the emulsions sometimes have flaws because, a mosquito landed on it during drying process. But it didn't look like a mosquito. It didn't have 6 legs or anything like that. It didn't look like an arachnid. It looked like a star, okay? So he went outside, and it was still dark, and sure enough, there was a naked eye new star in the vicinity of the Large Magellanic Cloud. So he got a lot of glory for that, and he announced the discovery very early, and so astronomers were able to study this thing just as it was evolving, just shortly after it was born. And you can tell a lot about the explosion by looking at it shortly after it was born. There it is before. This time they warned us which one it would be, and there it is after. Okay, so it turned out to be a type 2 supernova. You can't tell from this spectrum, but this is a really cool photograph anyway, and so I thought I'd show it. But it's a type 2 supernova. So it's the kind which we think comes from a big, massive star. Okay, so this is a chance to test our theory. First, Did it or did it not come from a supergiant star, a massive evolved star? Well, it did. There's plenty of photographs of the Magellanic Clouds prior to the explosion, and there is the star that is no more. And from a combination of photographs, you can tell that it indeed is a supergiant star. So that was basically confirmed. Interesting little twist. It was a blue supergiant, not a red supergiant. Slightly smaller than a red supergiant, slightly hotter as well. We think that's because the Large Magellanic Cloud doesn't have as many heavy elements as big galaxies do, because the big galaxies have had more supernovae and they tend to trap the gas. Whereas little galaxies, the gas gets all ejected. And so you don't get as much of a chemical buildup of the elements. And that affects the structure, the atmosphere of a star, which in turn dictates its size. So this was wonderful because our main prediction was confirmed, but nature threw us a new twist, which we had not anticipated, and which we had to figure out. Why was this thing a blue supergiant, not a red supergiant? Okay, next prediction. Were heavy elements seen, newly produced heavy elements? Well, this is a rocket sent up above Earth's atmosphere where it can detect gamma rays. And it turns out that some of the newly synthesized elements that you expect from a stellar explosion are radioactive. They decay into more stable things. In doing so, they don't take very long. They're not very stable things. And so after a few weeks, there isn't this stuff left. In particular, I'm talking about a radioactive form of nickel and a radioactive form of cobalt. They don't stick around very long. But radioactive nuclei emit gamma rays of a certain energy, which is essentially a fingerprint of that particular nucleus. No other nucleus produces exactly those same kinds of high energy photons, gamma rays, basically more energetic than X-rays, but otherwise the same thing. So you can tell that you're looking at a particular nucleus from its gamma ray spectrum, essentially. And what astronomers saw were gamma ray photons that could only originate from short-lived radioactive forms of nickel and cobalt. They couldn't have been there when the star formed 10 million years ago, because if they were there at that time, they're gone after a few weeks. Everyone will agree that a few weeks is short compared to 10 million years, okay? So there is no way that these things could have been in that star prior to the explosion. They had to have been produced by the explosion itself. And this is the primary evidence by which astronomers can really say with quite good certainty that heavy elements are built up inside stars. It's this kind of evidence, plus our inability to, despite extensive searches, to identify any other process in nature which produces heavy elements. In other words, this is a way of doing it, and it's the only way we know of doing it. Okay? So that's then a pretty powerful argument. All right? So that was very good. It confirmed this explosive nucleosynthesis. Third prediction. Did it basically form a neutron star? Did a core of iron collapse? Well, the neutron star might remain hidden for a long time by the blast of stuff that's careening outwards. But maybe you could detect something that was formed at the same time as the neutron star, this flood of neutrinos. Well, neutrinos don't interact with very much at all. But given enough stuff, in this case water, and given enough neutrinos, a few of them will interact. It's a statistical process. Half of them will make it unscathed through a light year of lead. The other half will actually interact. And if you've got a big enough tank of water and you've got enough neutrinos, a few of them will interact. So it turns out that for completely other purposes, there are these giant underground tanks of very pure water in several places, in the US and in Japan and in the former Soviet Union. And they have been basically constructed to measure a prediction of grand unified theories of physics. And one of those predictions is that the proton should be an inherently unstable particle. It should have a lifetime of 10 to the 30 or 31 years. So don't get too worried that your body is going to start disintegrating away. Our universe is only 10 to the 10 years old. But again, given enough protons, a few of them will do it sooner, a few will do it later. And they're trying to find the ones that are doing it sooner here. Well, they haven't detected proton decay yet. They've actually set very interesting upper limits. or lower limits to the lifetime. It's now upwards of 10 to the 31 years, getting close to 10 to the 32 years. That's very interesting physics, but they haven't actually detected anything yet. The most exciting thing they've actually detected, it turns out, are neutrinos from the supernova. A few of them hit the electrons and the protons in the water, gave the electrons a lot of energy, okay? Those electrons go zipping through the water, get this, at a speed faster than the local speed of light. Now you might say, what a bunch of hogwash from Berkeley. You were taught on your mother's knee that nothing can travel faster than the speed of light. That's true in a vacuum. The vacuum speed of light is the maximum possible speed. But light slows down in water or glass. Indeed, it slows down by different amounts depending on the wavelength or color, and this is precisely why we get a rainbow, okay? So it turns out there's nothing in physics that prohibits particles traveling faster than the local depressed speed of light, but not faster than the global vacuum speed. And these charged particles that go zipping through the water as a result of being hit head-on by a neutrino cause the electromagnetic equivalent of a sonic boom. Now, you don't hear those much anymore, but when I was a kid, you know, planes were allowed occasionally to go faster than the speed of sound. You'd hear these big booms. They were really annoying, which is, I think, why they don't allow them to occur, except for military aircraft nowadays. But it's electromagnetic equivalent. It's called Cherenkov radiation. It's just light. It's a blue kind of light. And it's detected by all these little photodetectors lining the sides of this tank of water where scuba divers go looking for conch shells and things like that. So they don't find very many of them because it's ultra pure water. Anyway, so there were two active experiments going on, the Irvine, Michigan Brookhaven experiment in the US and the Kamiokande experiment in Japan at this time. Both detected about 10 neutrinos. One was 8, one was 11, and they arrived right when they were supposed to, in the sense that if the star produced them 170,000 years ago and they travel at or close to the speed of light, they would have arrived about when they did. And at no other time have those experiments ever seen a burst of 10 neutrinos. So the circumstantial evidence is pretty darn good. It's like Mark Twain once said, if you find trout in your glass or something to that effect, you know, I forgot the punchline. I'm sorry. So something to that effect. Okay, so neutrinos are produced, and that suggests that a neutron star was produced, at least temporarily. Now, we know that the Crab Nebula, the great supernova of 1054, produced a neutron star. It's that little guy right there. I have a close-up of it here. It's a neutron star that's spinning very rapidly and emitting two oppositely directed beams of radiation that are not aligned with the rotational axis. So this thing is spinning kind of like a lighthouse, and we happen to be lucky enough to be in the beam of the lighthouse when it intersects us. You know, so we're not off here somewhere, in which case we'd never intersect it, okay? So we're in the beam, and we see it pulsing, and it pulses 33 times per second. And so here it is when it's pointing towards us, and here it is when it's not pointing towards us. So that's very good evidence for a neutron star, it turns out. We have seen no such pulsar in the middle of the remnant of supernova 87A. Now, admittedly, it's still cloaked by material surrounding it that's still expanding away. You know, there's like a curtain still around it. But holes are beginning to form in that curtain, and some astronomers think that maybe we should have seen the pulsar by now if it were there. So others say, well, okay, maybe the neutron star simply doesn't have a big enough magnetic field, or whatever it is you need to form a pulsar. Well, even then, if there's a neutron star, you'd expect some fallback of material, and you'd expect the supernova to be glowing right now more than it is. So some astronomers think that maybe, even though a neutron star did form temporarily, as indicated by the neutrinos, because if you have direct collapse to a black hole, you have no way of making neutrinos, okay? So we saw the neutrinos, so there was a neutron star for a while, but maybe enough material fell back onto the neutron star, caused it to exceed its stability limit, and caused it to then further collapse to a black hole. In which case its picture might look something like this. And this is my prize-winning photograph of a black hole. I'm quite willing to sell it for large green bills if you'd like to buy it. Okay. Well, really a black hole, of course, is a curvature of space and time, and it can be thought of almost like a pit into which if you fall, you can't get out, basically because the sides of the pit are too steep to crawl out of. This isn't a talk about general relativity. I'll be glad to talk about that someday, but it's a great thing. I mean, black holes, they're fantastic things, and we really do think they exist. We're not sure in the case of 87A yet whether there's a black hole there. Maybe there is a new black hole in the Large Magellanic Cloud. Maybe not. But we do have other evidence for the existence of other black holes. So we keep looking, hoping to see the pulsar. Meanwhile, of course, the supernova has shown us all sorts of interesting things. These are rings of gas that were actually ejected in almost like planetary nebula-like puffs by the star prior to its colossal explosion. So by studying these wisps of gas, there's the supernova itself. These are foreground stars. But these are wisps of gas that were ejected prior to the supernova. So by studying them, we could come to some understanding of what the outer layers of that star were doing just before the explosion. It's quite puzzling still how this triplet of loops has formed. But very recently, with Hubble Space Telescope, we've seen evidence that the innermost ring is beginning to brighten again. The fastest of the moving gases in this colossal explosion are beginning to reach the ring, and they're colliding with it, okay? It doesn't look like it here because here you see the densest gases which are moving slowly. But there are faster gases moving out here, and here's now a more recent picture. Again, you can see that the supernova is beginning to spread apart. See, it looks like there's almost a hole in it there. But these are the densest gases. Less dense gases, which are less easily visible, are beginning to make this thing and other little blobs on this ring begin to brighten up. And in the next few years, the supernova is going to undergo a renaissance, which I'm sure you will read about. If not in the New York Times or San Diego paper, you will certainly read about it in Astronomy and Sky and Telescope magazines. Okay, I'm not sure it'll make, front page regular news, but and it won't become as bright as a naked eye object, but it'll brighten considerably, especially at X-ray and radio wavelengths, and to some extent in the optical as well. So we're going to witness the collision here, and that will be just sort of a spectacular thing to see. So we're learning lots of things from this particular supernova. We pretty much confirmed our basic idea of how big stars explode, and we were thrown some new little twists. This particular star didn't tell us anything about how the type 1s explode, except that they're probably different from this explosion, okay? And that's good, we know that now. We're going to continue learning from this event, but I'm excited about supernovae in part, not just because of the elements that they produce, but also because of their utility for cosmology. Here's a supernova in a nearby galaxy whose distance we know. This is a star in our own galaxy, by the way, 500 light years away, 50 million light years away. Youch. There's a star brighter than a star in our own galaxy, yet it's 10 or 100,000 times more distant. Anyway, so that's one star going off in this galaxy. We know its distance. We can calibrate how intrinsically bright that explosion is. We can then compare that with the apparent brightness of very distant explosions of the same kind. These are in particular the type 1 supernovae. And so we can judge the distance of these really distant ones compared to the nearby one. Like nearby headlights, bright, distant headlights, dim. Great. As long as you know the distance of the nearby headlights, you then can determine the absolute distance of the distant ones. So the upshot is that we found that these particular supernovae are in galaxies that are too far away. And by that I mean that they're farther away than they could have gotten in the time since the Big Bang if the universe were not slowing down at all. So, really, usually you expect things on their upward path to slow down because gravity is pulling on them. Whether they continue to escape from Earth or not depends on the speed with which you heave it, but you always expect them to be slowing down. Well, suppose the Earth had no mass and you just heave this ball, then it'll go at a constant speed. There's nothing pulling it back. What we're saying is that these objects are farther away than they could have gotten had they been going even at a constant speed, and definitely much farther away than they could have gotten had they been slowing down. And of course, there's the other question of there's a big bang and big crunch, and definitely they're not doing that. They're moving away from us even faster than we expected. And that means that the universe's expansion is speeding up with time. And this was deemed by the editors of Science magazine to be the breakthrough of the science breakthrough, not just astronomy, but all of science of 1998. We're still not sure we're right, but in the 2 years since we announced this result, it hasn't gone away, and in fact, it's gotten stronger. And I'll tell you in a few weeks why Einstein looks so surprised. But he, in a sense, predicted this effect and then retracted it because he called the effect itself his biggest blunder. And now it turns out that his biggest blunder may have been one of his greatest triumphs, actually, which is even more of a reason for Time magazine to have voted him Person of the Century. Although if you read that article, nowhere do they actually use this particular argument. So he was worthy enough even without this, okay? I talk about it quite a lot in this series of tapes that Dennis mentioned with the teaching company. It's easy to remember, 1-800-TEACH-12, okay? Not too hard, www.teachco.com. The reason I'm telling you this is that their president is really interested in people who like astronomy from the amateur perspective or whatever, and he says that anyone who comes to hear one of my lectures, like here, is deemed to be a friend of Alex, okay? And you get the special Friend of Alex price. These tapes, 40 lectures, 45-minute lectures, are typically $500 total. If you're a friend of Alex, you get it for $200, okay? And all you have to do is call them up and give them the code. You don't say friend of Alex. Well, you can say that, but you say friend of Alex 9922. That's what you tell them. And they'll give it to you for $200, which is a pretty good deal. But anyway, if you're interested in cosmology and galaxies, I have 16 lectures on that. Supernovae and black holes I have a couple of lectures on, and 40 on all of astronomy. And you can find out a little bit more about this expanding universe, black holes and supernovae from this course. I'm proud to say that we actually made the discovery of the expansion rate being faster and faster before I taped these lectures. We didn't understand it quite as well. Of course, we still don't understand it. But anyway, supernovae are fun. Astronomy's fun. I thank you all for your attention, and I'll be glad to answer questions as long as you'd like. Oh yeah, the implosion of the Type II, actually the core, which is only about the size of the Earth, takes something like just a small fraction of a second to implode. The rest of it, of course, takes a much longer time. And in fact, it takes a while for the outer atmosphere to even realize that anything has happened in the middle, because it's as though, suppose the middle collapses. What could transmit that information to the surface layers? Well, it would be a pressure wave. It would be a sound wave. And that wave travels at a relatively slow speed. So in fact, the shock wave from the rebound turns out to be faster than the regular old sound wave. It's supersonic, so that gets the information out in a reasonable amount of time. But it still takes the better part of a day for the outer layers to find out that something's gone on in the middle, assuming they haven't caught any of the neutrinos that have gone zipping out, okay? So depending on the size of the star, it takes from a few hours in the case of 87A, because it was a blue supergiant, to about a day in the case of a red supergiant. But the collapse of the core is less than a second. Yeah, that's, suppose parts of the collapse sort of missed each other, The way they might miss is if the core is already rapidly rotating. In that case, the collapse of a rapidly rotating thing can lead to a disk-like structure, and maybe that would be an unstable configuration for a neutron star, and it would then go and become a black hole, even below the usual stability limit of a neutron star. We don't, however, think that a piece can overshoot another piece and go flying away, this kind of disintegration that you're talking about. It's an interesting idea, but when you do the calculations, it turns out that there's too much stuff, in a sense, bearing down on all this to even allow things to, little bits and pieces, to escape out. So we think they either form a neutron star or a black hole, and possibly the latter in two stages. First neutron star, then black hole. Let me take one from the other side here, and then, yeah. Yeah, Betelgeuse, oh yeah, it'll be bright. But Betelgeuse is pretty far away. I believe it's 520 or something light years, or 1,500. it's some goodly number of light years away, and it won't actually hurt us. You need to be something in the vicinity of 10 light years away for a supernova to cause really serious damage, maybe 30 light years. And if you calculate sort of the history of the Earth, how close has it been to exploding stars? And it's a probabilistic calculation. You calculate that in the history of life on Earth, maybe at one time it was close enough to an exploding star to have been affected. So maybe one of the many mass extinctions that are known about was produced by a supernova. Interestingly, maybe one of them was produced by a gamma ray burst as well. That turns out to be roughly the same frequency as supernovae. I mean, they're less frequent per galaxy, but their radiation is much more powerful, at least in the beam in which it's directed. And so you get soaked in a major way. Sunblock 50 doesn't help you, even from a considerably greater distance than 10 light years. So the integrated effect of gamma ray bursts turns out to be about as lethal as supernovae. And they are not as lethal as comets and killer asteroids, and perhaps even gigantic volcanic events on Earth, like the ones that gave rise to the Deccan Flats in Asia. So probably most extinctions are not due to supernovae and gamma ray bursts, but possibly some of them were. Yes, back there. How accurately can we predict a precursor of a supernova? In the case of the supergiant stars, we would say pretty well. If they're massive enough, they have almost no choice, okay? So if we can measure their mass, which is actually kind of a tricky thing, the way you do that usually is by measuring stars in binary systems, but not all supergiants are in binary systems. Anyway, so if it's a supergiant, we think that we can say, hey, that's probably going to become a supernova. The ones that come from white dwarfs in binary systems are a much more tricky business, because there you need a white dwarf that's close enough to a companion star, and second of all, it's going to have to steal material from that companion star at a rate which is compatible with a steady buildup on its surface and not with the nova process. And moreover, for certain other rates of accretion, what could happen is a process called accretion-induced collapse. The white dwarf basically undergoes a collapse to form a neutron star. The protons and electrons combine to form neutrons and neutrinos, but without really a visible supernova. So the details of that are really very poorly understood. And I think it's very safe to say right now, few of my colleagues would disagree with me, that we know that a type 1a comes from an exploding white dwarf, but we don't know how the heck it actually got to the Chandrasekhar limit. Because there's so many ways it can avoid getting there. And all these ways of avoiding it means that there really should be far fewer type 1as than we even see. So somehow stars manage to get to the explosive state, and we don't really understand how they get there yet. It's a research topic ripe for a PhD thesis for a very ambitious student. So yes. Yeah, the rings formed before the star exploded, yes.
So how come you don't look for the rings?
How come you don't look for the rings? Magnificent question, actually. The rings were lit up by the flash of radiation that was emitted when the shock wave first burst through the surface of the star, heated it to a couple of 100,000 degrees, and said to the surface, hey star, here surface, I've exploded, okay? You know, this shock wave comes in, it's like, you get hit by a big enough wave of air, and you actually get heated up by this. So it heats the surface of the star for a short time to a couple of 100,000 degrees. Objects at those temperatures emit a plethora of ultraviolet radiation and X-rays. Those X-rays and UV rays then ionized and excited the quiescent, dark, cold rings sitting around it, and that is what has made them glow. There are surely supergiants out there that have these rings around them. We just don't see them. So some astronomers, because they haven't been lit up yet, you see? They only get lit up at the time of the explosion. So before the explosion, you can't tell that they're lit up, because they're not lit up, in fact. So, that's a tautology there, right? So some astronomers are now trying to figure out ways of detecting them, like if molecules form in these clouds, then you might see molecular spectral lines. And that might be a bit tough. Molecules we think form in more dense environments. But at least hydrogen molecules can form sometimes, or at least hydrogen itself has the so-called 21 centimeter radio line. It has to do with the way the proton and electron are spinning. If they're both spinning together versus opposite directions, it's a slightly different energy, and when they flip back and forth, they emit radio waves. It's the kind of waves that many people are using to search for extraterrestrial intelligence, just because we figure that other intelligent creatures will recognize the importance of that part of the radio spectrum and will choose to transmit near, at about those frequencies. Anyway, be that as it may, the hydrogen in a cold disk could someday be detected, but you need very sensitive radio telescopes to detect these cold disks. But you're absolutely right, they're out there and they could actually tell us which ones are perhaps about to blow. Yes?
Well, just keying off that, could
Yeah.
you use the source of ultraviolet, a nearby nova that you know about, and say, is the intensity enough within a few light years?
Here's the problem, great idea. The trouble is space is amazingly empty. And a nova flash, bright though it seems to us, actually is fairly puny compared to a supernova, and it doesn't light up much of the space around it. So the chance of having a massive red supergiant nearby is small. I mean, you can count the number of red supergiants in the sky pretty easily, even though they're the most luminous stars, and you see them, if anything, to much greater distances in our galaxy than you see other stars. Admittedly, many of the bright stars are red giants and supergiants, but the galaxy is not mostly red supergiants. So the space between them is basically empty. You're unlikely to have a nova near one. If you do have a nova near one, fantastic proposal. Your method would work. Okay? Or if you had a supernova, that would light up a bunch of stars in that galaxy, but there you've got the problem that supernovae are rare in any given galaxy. So when they do go off, they light up a pretty big volume of space within that galaxy. But in our own galaxy, we've been waiting 400 years to even see one, let alone see what it lit up in its vicinity. Yes? He's a brilliant programmer, yeah. Well, he's a brilliant programmer. He had time, he had energy, he had the knowledge, he had the enthusiasm. That combination was superb. And again, I'm sort of a cheerleader and a fundraiser, it seems, most of the time. I wish I could spend more of my time actually dealing with the nuts and bolts instead of just thinking up the projects and talking about them. There's a hell of a lot of people who do the work behind all these slides. And indeed, much of what I talked about today wasn't even my own research group's work. I mean, Supernova 87A was in the southern hemisphere. I'm an observational astronomer. I have teaching duties and stuff. I couldn't really go and camp out in Chile for a few years. Berkeley wouldn't have really liked that. Moreover, there are observers there who are poised to do that kind of thing. One of these days, we'll have our chance here. And indeed, in 1993, we had a very good supernova in M81, a galaxy many of you have certainly looked at in the Big Dipper. It was a supernova called 1993J. It was a wonderful thing. I had a great time doing it. And in fact, one of my students is just completing his doctoral thesis analyzing 6 or 7 years worth of data that we've gathered on supernova 1993J. So interesting, it was at plus 69 degrees declination, and 87A was at minus 69. So they were almost, same declinations, but opposite parts of the sky. I don't know. Those of you who are into numerology can do whatever you want with that statement. Yeah. Eta Carina, yeah, weird star. Eta Carina is down there in the southern hemisphere. It's estimated to be between 1 and 200 solar masses. In fact, the theoretical limit is between 60 and 100. So you wonder, how does it do that? Well, there are exceptions to many rules, it somehow has managed to form itself in a quasi-stable state. And we think it's not yet at the supernova stage. We actually think that deep in its core, it's just about done burning hydrogen, and soon will start burning helium. If that's the case, it's still quite a ways from supernova. If, however, it's already done burning these light things and it's nearly ready to make an iron core, it could go off any day. We're just not sure of its state of evolution right now. But it's a good one. Hey, some astronomers like to say that's going to be the next supernova in our galaxy. Yeah. Yes. Mm-hmm. Yeah, let me just elaborate a little bit on your first thing, because it may be basic, but it's so fundamental. In fact, in my class at Berkeley, I say that there's a few things you've got to learn, and here's one of them. The finite speed of light is a wonderful thing because it allows us to see different parts of the universe at different stages of time. Light travels at about a foot per billionth of a second, a foot per nanosecond. So I see Herb as he was about 10 nanoseconds ago. He might not even be here anymore. Oh, he is. Good for me because I have more of an audience, even better for Herb, okay? So we see the sun as it was a little over 8 minutes ago. In fact, we see the moon as it was about 1.5 seconds ago. And indeed, if you go back and watch tapes of the lunar landings, you know, Neil Armstrong and Buzz Aldrin stepped on the moon, and Neil Armstrong stepped first, you know, for whatever reason. Interesting story there. There's all these pictures of Buzz Aldrin. No photographs of Neil Armstrong. Why is that? Now the legend, maybe it's an urban legend, is that, you know, they took pictures of each other, but that Buzz accidentally forgot his camera on the moon. And that's why there's no pictures of Neil Armstrong. I don't know. But there aren't. He was apparently upset that he was not the first. But anyway, okay, so Neil Armstrong stepped on, and Mission Control in Houston said, "How does it feel, Neil?" Yeah, and a few seconds later he goes, "Oh, good, good," you know, and you think, is he suffering from oxygen deprivation? You know, usually when you say, "How's it going, Chuck?" you get an immediate response. Usually it's pretty good, you know, Al or whatever. Even if the person's feeling like crud, you know, they say pretty good. You know, you want to be pleasant, you know. You don't usually think for 3 seconds. Well, the reason this happened is that it took 1.3 seconds for the light rays, actually radio, to reach Armstrong. He answered as quickly as he could, but it took another 1.3 seconds for the radio waves to come back, for a total round-trip time of at least 2.6 seconds, and hence the delay, all right? Anyway, so we're seeing the moon as it was about 1.5 seconds ago, the sun 8.3 minutes ago, the nearest stars 4 or 5 years ago. Now, extrapolate this and look at galaxies millions and even billions of light years away. You're seeing them as they were millions or even billions of years ago. And if you find a galaxy that's 12 billion light years away, and the universe started out, I mean, at a time and now has an age of 14 billion years, you're seeing it as it was when the universe was only 2 billion years old. So you're seeing a young galaxy. And we can compare that with galaxies we see effectively here today to within a couple of million years, compared to a billion, who cares, you know? It's like Bill Gates, you know. What does he care if he had a little hole in his pocket and a few million leak out? There's this calculation. How big would a bill, an actual monetary bill, not Bill himself, have to be for it to be worthwhile for him to notice someone on the street, stoop down, and pick it up? It turns out to be quite a large bill, something like $10,000 or something. Anyway, so we see these galaxies as they were when the universe was 2 billion years old, and now it's 14. We see other galaxies at intermediate stages. If we assume that typical galaxies today were like typical galaxies long ago, but just young back then, we can sort of say on average what galaxies looked like back then, and on average then how they evolved. So this business of looking back in time is definitely a fundamental concept, which is one of the tools that astronomers use. And so going back then to your question, the supernova of 87 really exploded, you know, now 13 years ago, roughly, plus about 170,000, and that actual number is quite uncertain because we don't know the distance of the Large Magellanic Cloud to better than 2 or 3 significant digits. Is it 173.5 thousand light years away, or is it 174.2 thousand light years away? Well, we don't know. But in a sense, we don't care exactly when that star went off. We care when we observed it. We do care when it was that the light from distant galaxies was emitted, but then when you're talking about 10 or 12 billion light years, who cares if you make an error of 10 million years? You know, again, those are all small errors compared to the main effect you're trying to see. But indeed, the bottom line is that it is conceivable that some of the stars that you see are no longer there. Now, in fact, very few of the stars you see are likely to be close enough to their deaths that they will have died between the time that they emitted their last photons, and the ones that we're seeing now. Most of the stars you see are within a few thousand light years of Earth. And it's simply statistically unlikely for a star to be within 1,000 years of its death out of a 10 million year lifetime. Okay, it's all a question of statistics. But it is possible that some of the stars have already died. Neat idea, neat question. Do we test whether they're uniformly distributed throughout the sky? We actually don't do this test because we have this incredible pollutant in the way, our own galaxy. And even away from the Milky Way, there's some dust and gas. So we try to stay as much away from the Milky Way's plane as possible. With these big telescopes, we can only survey a small fraction of the sky anyway, because there's just not enough time available. So we choose the best parts of the sky to look at, the ones least polluted. Now, if we only chose one part of the sky, you could very well argue, how do we know that the whole universe is accelerating its expansion? How do we know it's not just that direction which is messed up? Okay? Indeed, there are things like the Great Wall and other non-uniformities in the universe which could be tugging us to or fro. Well, we have done enough lines of sight out of our galaxy to have seen that in the 5 or 6 that we've chosen, in quite opposite directions of the sky, the effect is the same no matter where we look. And that gives us some confidence that if we were to look at every single square degree in the sky, and there are 44,000 of them or so, or 42,000, we would get the same answer. I'd love to get enough telescope time to examine every single square degree, but hey, I don't. Yes? Mm-hmm. Yeah, I know. Yeah. I mean, Lick Observatory is nice because it's a 2-hour drive from Berkeley, especially during the developmental stages. We had to kind of go up there back and forth. People have asked us, why don't we put it on the top of Mauna Kea, in Hawaii, which is a really great site, or on the Canary Islands, or in Chile. Well, I don't have the time or the funding or the inclination, to tell you the truth, to go back and forth to Hawaii or Chile all the time, or even to Mount Laguna, family, and teaching duties, and just, the wear and tear of travel. So Lick is convenient. It's not a great site. It is the first mountaintop observatory. It was built over a century ago when the concept of having telescopes on remote mountains, at that time remote, not with Silicon Valley the way it is today, but it was a day-long carriage drive, horse and carriage, up to the top. It was very remote. There were squatters up there who wanted to take the land, and they had to be basically, chased away with rifles or something. Probably the regents did something bad, but that wouldn't be the first time, so. Anyway. Okay. Well, you've been a great audience. Fantastic questions. Thanks.